All right, so we are going to talk about colorimetry and spectrophotometry, and this is one topic that's not covered in a typical college chem course, but it's specialized for AP Chem. We're going to focus on the highlights. One of the packets that you have is the slide presentation. The other packet is a pre-lab, which each student must do individually. If you sit down and do it amongst your group, submit all of yours together, but each person needs to do one and submit one because it's a critically important concept that I want to make sure that you have mastery in, because it's something that you will see on the AP Chem exam, either in the multiple choice section or potentially on the Part 2 section. So you want to be comfortable with anything dealing with spectrophotometry. The slide presentation I nabbed from someone, I can't recall who, although I should give him or her credit, so I'll try and go back and look who the author is. That lab for period 7 is due Thursday. And let me just remind you that you have a lot of chemistry. For period 7, you are quizzing tomorrow. Your Le Chatelier's principal lab is due on Wednesday. That's the lab we did the other day. If you were out, we filmed it in second hour. It's already posted. If you want to go back and look at the colors, it might be helpful to you as you write it up. Your test is on, I think I have my days wrong. That lab for period 7 is due Tuesday. This little mini thing, which won't take very long, I'm going to walk you through a lot of it toward the end today, is due Thursday. Your test is on Thursday. A lot of chemistry coming down the pipe. Yes, it's like bam, bam, bam. Your test really should be Tuesday, but I want to get your quiz to you. All right, with colorimetry and spectrophotometry, we're going to introduce some basic concepts to you. A lot of it you have seen already in previous chapters. Uh-oh, that's my laser pointer. What happened? There we go. So colorimetry is essentially just using your eyes, and you can somewhat assess the concentration of a species if it's colored. When I say somewhat assess, think about it this way. You make lemonade and it just tastes too tart. You might take some of the lemonade, mix it with some water, you'll dilute it. The lemonade that's very yellow is more concentrated than the lemonade that's just a little bit yellow. Or, I hate to use this example, but it's perfect. When you go pee-pee in the morning, it's a yellowy orange color, and then after you've had a lot of water to drink, it's not nearly as yellowy, right? So, the darker the color, the more concentrated the solution, provided that you're comparing the same substance dissolved in solvent, typically water. So colorimetry you can just see. Nothing special in regard to materials that you need or any type of technology. With spectrophotometry, this is where you're going to use an instrument. You're going to use a spectrophotometer to make the same kind of measurements. Now, typically what you'll be measuring is either the percent transmittance, which we'll get to in a minute, or the absorbance, and then you can relate it to the concentration, and you actually can determine an exact concentration of a solution, and we'll be taking a look at that. Again, initially you're just going to have a pre-lab, and then we're going to go through the acid-base chapter and do some fun labs in there. And then we're going to come back to this concept once you understand spectrophotometry and use the spectrophotometers. I already mentioned visual observation. We know visible light is just a very narrow range of the electromagnetic spectrum. The wavelength for visible light, the whole Roy G. Biv, is from 400 to 700 nanometers. And we'll put that into perspective in just a minute. Again, there's your visible region right there, a very small region of the electromagnetic spectrum. highest energy gamma rays, lowest energy radio waves. You should recall that energy and frequency are directly related. So the higher the energy, the higher the frequency. Frequency and wavelength are inversely related. The greater the frequency, the smaller the wavelength. And that's shown here, and we've seen this image before. This also goes back to something that we talked about previously. The types of radiation are indicated on the left, their frequency, their wavelength ranges, and then the type of transition. And you probably recall that microwaves are molecular rotations, because we talked about how the microwave plate rotates, and you can get the molecular rotations as opposed to the vibrations that we looked at previously. Also, you'll recall that X-rays are required to eject electrons that are in innermost shells, that are core electrons, and we talked about that as well with PES previously. We know the relationships between energy and frequency, and between frequency and wavelength. The longer the wavelength, the lower the energy. If we look at a color wheel, you can see colors that are complementary. This is complementary, like peanut butter and jelly go together. I never ate peanut butter because that's yucky. But, you know, certain outfits have complementary colors. They look nice together, others more clashing. For those of you who are in art classes, you're probably much more familiar with this. But when they lie across the circle, they are complementary. For example, yesterday in the lab, or whenever I saw you last, we had orange color solutions. That's because they reflect orange, but they actually absorb blue light. And we'll be looking at that aspect of absorption with the same solutions we were using the other day in the lab in a couple of weeks. Who took AP Bio? In AP Bio, no pressure, honey, you probably remember with photosynthesis and electron transport chain, there were two photosystems, P680 and P1 and P2, and one of them was at 700 nanometers and 680 nanometers, and those were red. But what color does chlorophyll reflect? Green, because plant leaves typically are green. But they absorb red light, and you can see the red and the green on opposite sides of the color wheel, and that's because they're complementary as well. And there are the complementary colors there, and again I said, remember 700 nanometers for that red absorption there, and we'll be dealing with the orange-blue as well in the lab, and that's what we'll be setting our spectrophotometers out. We'll have a blue filter. If you were to look at solutions showing increasing color, you can see it more clearly here. This solution would be more concentrated than this, but in colorimetry you can only make a comparison. You can't pinpoint a concentration. You can just say what is more concentrated than the other. And you can also see here between red and blue in terms of their ratios, and here you can see that you get the purple color here. We'll come back to that in just a sec. This is going to look confusing, but we've actually already calculated concentrations using dilution. You saw it previously as M1V1 equals M2V2, or as M stock V stock equals M nu V nu. They're just using C for concentration. We used M for molarity, which is your typical unit of concentration. So you can calculate the concentration of a dilute solution by multiplying the concentration and volume of the standard, or the concentrated one, over the volume of the dilute. And I'll give you an example of that in just a minute, but it's very simple to do. This is far too complicated and probably should come out. When you're talking about light intensity, what we're going to look at, I think it's a little easier in a different slide. I'll come back to it in a sec. As I said, the instrument that you're going to be using in the lab in a couple weeks is the spectrophotometer. That's going to measure the amount of light absorbed or the intensity of color at a certain wavelength. The intensity of color can be given a numerical value when you compare the amount of light that you start with the amount of light that passes through the solution. And transmittance and absorbance we'll hit in a sec. There are two different types of spectrophotometers, one in the UV region. We don't have those in high schools. We have a few visible light spectrophotometers, and they're going to have wavelengths in the visible light region. One way that you can determine concentration from absorbance is using Beer-Lambert's law, shown here. This equation is given on your formula sheet for your AP exam. A for absorbance, this is what you're going to measure using the spectrophotometer. Little a, it also can be an E, like an epsilon. This is your extinction coefficient or your molar absorptivity. Typically it's a constant, although in your pre-lab you're going to calculate it. B is the path length in centimeters. This is the diameter of the cuvette. The cuvette is the glass tube that holds your sample. And C is for concentration in molarity. And we're going to use Beer's law to calculate the concentration of different solutions, and that'll be based on their absorbance. So for example, with transmittance, transmittance is I, that's the intensity of light. Let me pull it down here. You start with some initial intensity of light, so you shine light on a sample, and then you measure the amount of light that goes through. If you divide the amount of light that goes through over the intensity of light that you began with, you get the transmittance. And then if you multiply by 100, you get the percent transmittance. The absorbance is just negative log of T, or there is another formula that you can use, and I'll walk you through that in a minute. The path length, again, is the diameter of the cuvette. There are several calculations or equations here. You don't need to be familiar with any of them, to be honest. I'll walk you through what you need to know in just a minute. The absorbance for this sample is 0.0227. I think I missed a 2. 0.02227. And I'm going to leave that there because it's too complicated. This is a Spec 20. This is exactly the instrument that we're going to be using in class. I'll go through all the different pieces in just a minute. Abbreviated as a Spec 20. You're going to have a tungsten filament lamp, and that's going to emit visible wavelengths of light. I'll teach you how to blank the machine out when we do it. This is what's happening inside the spectrophotometer. You have a lamp, so you're getting light. There's a lens, a monochromator. Here's your sample. So you have light in, and you're going to measure the light that goes through the sample. So clearly, the deeper the color, the less that will go through. Less will be transmitted, more will be absorbed. And this is far more information than you would ever want to know about spectrophotometry. Here's your machine, and again, when you use it, it'll make more sense. I'm not going to ask you questions about this, but we will set our wavelength here. We'll have a filter set to go. Our sample's going to go in here. We're going to initially have 100% transmittance, and then we'll flip it to absorbance. This is our digital display. This came up several years ago on some AP exams. It's actually common sense because you're very good at math and interpreting graphs. I don't think you'll have an issue. It says plots similar to the three below will need to be generated using a computer program such as Excel. I'm not going to ask you to do that. If you were given these plots, you could figure out the optimum wavelength. For example, if you measured absorbance and plotted it versus wavelength, so basically you measured absorbance at different wavelengths for a certain colored sample, you will see that blue dye will peak at 620 nanometers. So that's the wavelength that you should measure blue dye. For example, red dye will peak maximum at 520 or maybe about 515, and so that's the wavelength that you would set the machine out for red dye. Purple, you know, is comprised of both blue and red, so you can see the superimposing of the two different curves on that graph, and then here's the blending of them here. What you are going to plot in your pre-lab is the following. You have absorbance, which you'll measure off the spectrophotometer, versus concentration. Now, if you know what the absorbance is, you'll plot a curve based on, can't think of the word, control solutions. And then you'll use your solutions and read them off the curve. So you'll generate a plot such as this. You'll make a best fit line. You won't just connect the dots like first grade. And then if you want to know the concentration of the substance, well, if it absorbed 0.6, you just come across, you come down, and you have about 3.8 molar as your concentration. And you'll be generating a curve similar to this one. And I'm going to walk you through that in great detail. Just hang on. These are all applications for spectrophotometry, very helpful in blood analysis as well as food safety, RNA, DNA concentration, as well as other applications listed there. What I want to show you is your pre-lab assignment, which is not a big assignment. On Edline is a pre-lab on Beer's Law. Now this actually is the whole lab, so you don't have to read through the whole thing. There is some background information that I wish you would read cover to cover, but since the kids never did, that's why I put a little slide to show together, although it really would help you to read through the first page, the second page, and the third page, because that's just some background reading. In addition, on Edline, in your Notes tab, there is some very simple reading on spectrophotometry that probably would be extremely helpful to you. You don't have to read through the procedure because we're not going to do this lab or the post-lab questions. What you're going to come to is what I have given you already. So you need to do the pre-laboratory assignment, and we're actually going to get a little bit of it done now. It says read an authoritative source, and so that's why you're going to read through the first several pages of the lab. It says, explain why it's necessary to work with the 2.5 molar ammonia solution under the fume hood. What do you know about ammonia? It can be.
It's really like weak iron enough so that the vapor pressure is high.
Exactly, because ammonia, actually, that's actually a little misleading because ammonia actually has strong IMFs. It has the capability of hydrogen bonding, but nonetheless, it's highly volatile. When you open up a bottle of ammonia, you're like, whoa. So the ammonia is highly volatile, so it readily goes from the liquid to the gaseous phase, and as a result, for safety reasons, you would want to use you would want to open it up in the fume hood. And this probably is more concentrated than the bottle you have at home, although it comes up to 4 molar, so I don't think this is too bad. All right, in question 3, it says a student based the analysis of copper-2 in a sample on the formation of blue complex ion of copper and a standard solution of another complex ion that's hydrated. When 1.213 grams of pure copper wire was weighed, dissolved in nitric acid, and diluted to 100 mils. So you're going to need to get the concentration of the copper, and that's really just the copper or copper ion. That'll be your stock solution. So on the back of that first page that I have given you, there is this great little cheat sheet. Okay? And I'll come back to 3.1 in a sec, but 3.2 it says convert mass of copper to moles. What does it say? Convert mass of copper to moles. Oh, then it should say then molarity. That's a typo. Go away. Should say then. Does it say that on yours?
No, this is that.
Oops. Whee. How do I get that little thing out? Whatever. Oh, it should say then. I'm sorry. Get over it. Okay. So let's take a look here. One of the things we have to do is find the absorbance. So on the cheat sheet, it says 2 minus the log of the percent transmittance. Okay, let's do the first one. So we're going to have 2.0, oopsie, I'm in letter format. 2.000 minus LOG 89.95 equals. And maintaining our siggy wiggies now, we're going to have 0.046. That'll be our absorbance. And you can do that down this line right here. If we have a minute in Excel, we can pop those in and they'll all pop out, and that would be great. You need to figure out the concentration of copper ion in the concentrated solution. So you will convert the mass to moles, and you will divide it by 0.100 liters to get the concentration of the stock. To get the concentration of the dilute solution, you have the volume of the stock, you have the volume of water used. So what will be the total volume in each of these cases? 50.0 mils, okay? So what you're looking at, and this is on your cheat sheet, the new volume's 50, but now hopefully you understand better where it came from. You'll have the molarity of the stock, you know how much stock you used, you know the volume of the new or dilute, and you will be calculating the molarity of the new or dilute solution each time. And that's what you are going to plug in here. Okay? And you'll have a few secs to work through that. Then what you're going to do is you are going to prepare the calibration curve. So you're going to plot absorbance versus concentration. So absorbance on the Y. You'll draw the best line through and determine the slope. Be sure to indicate the units of the slope of that line. You'll calculate molar absorptivity using A is equal to baby ABC. And then the question that causes the most problem for the kids is this one. It says, explain why this method of analysis would or would not be satisfactory. Look at your curve. Can you clearly read that concentration off your curve? If you can't, if it's at one edge or the other, then the method is not satisfactory, okay? Also in that lab, or the little pre-lab packet that I handed you, and again, we'll have some time in class. I'm not sure if I'm going to start acid and bases after the quiz, or I may save some time the next period to work on it. I gave you graph paper, all right, so there's graph paper there. And then finally, in regard to the back, you're going to see an old AP style question, and it's still a really, really good one. So we'll reserve some time to address this either after the quiz or on the next block day. I'm just not sure how I want to break up acids and bases yet. It is a lot to take in, so I just like to break it up over very...
Wait, so do we do this or we just hold off on
No, no, no. You can do this at this point, but I'm going to give you some time. I would imagine what you're going to be doing tonight is preparing for your quiz. So this will not be on your quiz. That would be tremendously unfair. But this is due for period 7 on Thursday. So this hopefully gives you a better understanding of spectrophotometry. We're going to get into spectrophotometry more. I don't think I will include spectrophotometry on your test. You'll see it later in the 9 weeks.